Journey to discover the most impressive processes around the globe. Today, let's dive into the production process of laminated veneer lumber, or LVL. This is more than just a building material, it's proof of how humanity can spectacularly refine, multiply, and surpass the inherent limits of natural wood. Particle board isn't just an alternative material, it's like the Earth's response to the era of climate change. If wood waste is buried in landfills, it decomposes and produces methane, a global warming gas 25 times more potent than CO2. But if it's collected and recycled, this problem is significantly mitigated. For every ton of recycled particle board, we save around 12 mature trees from being felled. This preserves forests, provides a refuge for birds, and maintains the flow of biodiversity. What's more, particle board offers significant economic benefits. Compared to solid wood, it's cheaper and easier to mass produce. Consumers benefit, businesses save costs, and the entire supply chain becomes more seamless. It's a clear symbol of the circular economy, where nothing is discarded as waste, but instead, resources are simply waiting for a new purpose. Now, let's join Rawmachines for a deep dive into how this process works. Every piece of particle board starts with what seems like a worthless resource: dusty sawdust from the corner of a mill, wood shavings from a saw blade, scraps from old furniture, or even planks from dismantled buildings. Typically, softwood is the ideal choice due to its uniform structure and ease of processing. But occasionally, hardwood is also utilized, although it requires more effort and energy. After collection, the wood waste undergoes a purification ritual. A vibrating screen removes dirt, bark, and dust, while industrial magnets extract any leftover nails and staples. This ensures the finished particle board is pure and free of defects. Next, the wood particles are sorted by size. The coarser pieces form the core, while the finer ones are used for the surface layers. From its initial chaotic state, the material gradually enters a new order, ready for its rebirth. When the wood scraps have been cleaned and sorted, they are still rough, with long pieces, short chunks, and sharp broken edges. To become the standard raw material for particle board, they all must be chipped into uniform wood particles. This is where the massive drum chippers show their power. Inside, alloy steel blades rotate at speeds of 500 to 1,000 revolutions per minute, chopping large pieces of wood into small fragments in just a few seconds. But this isn't just brute force. Right after the chipping chamber, an integrated screen performs on-the-spot sorting. Any particles that are too large are returned for further grinding. Any that are too fine are rejected, as they consume too much adhesive without adding strength. Only those that meet the standard, less than 30 millimeters in size, firm enough, and compact enough, are transferred to the drying stage. In a way, the chipper doesn't just grind wood, it redefines its destiny. This is the first step in creating a uniform language, so that these tiny wood particles can speak with one voice, the voice of a completed particle board panel. But that's just the beginning. These wood particles are still full of moisture, like sponges. If they're taken directly to the press, the steam in the wood would rise, causing the entire panel to blister or even break apart. That's why drying is an essential stage. Inside giant rotary drum dryers, hot air is continuously blown at extreme temperatures, from 300 degrees to 570 degrees. The wood particles tumble and roll inside, and each layer of moisture is drawn out and turned into steam. The goal is to reduce the moisture content to just 2% to 8%, the ideal balance. Too dry, the particles become brittle and fragile. Too wet, the resin won't bond properly. The entire process is monitored by an online moisture sensor with precise accuracy, which only allows batches that meet the standard to proceed, while the rest are immediately rejected. After leaving the dryer, the wood particles are dry, light, and stable. But they aren't all uniform. Some are too large, while others are as fine as dust. So, they must go through one more round of refinement. On the conveyor, the wood particles enter a multi-level vibrating screen system. These massive stacked metal frames vibrate at a continuous industrial pace. The particles roll, slide, and jump through each layer of mesh, automatically sorting themselves by size. Particles that are too large are sent back to the chipper, while overly fine dust is discarded. Only the standard size particles are retained and then clearly separated. The finer particles are designated for the surface layers, while the larger ones are reserved for the core. This is the casting call, where each wood particle is assigned its proper role to help create a perfect board. And now we arrive at the heart of the entire process, the adhesive, the soul of the board. Inside a sealed chamber, the wood particles are coated with a fine mist of resin. This stage is commonly called blending, but it's more like a birth ritual. The resin acts as a new bloodstream, seeping in to cover every fiber, giving them the ability to bond. The two most common types of resin used here are urea formaldehyde and phenol formaldehyde. Urea formaldehyde is inexpensive, easy to use, and provides high adhesion, like a diligent builder, quickly getting the job done at a low cost. Meanwhile, phenol formaldehyde offers durability and resistance to water and weather, like a suit of armor for the board. Depending on the final product's requirements, engineers will choose the appropriate resin or blend the two. In addition to the resin, the blending chamber also adds sophisticated additives: wax for water repellency, flame retardants for fire resistance, and antifungal agents for a longer lifespan. Each component is like a craftsman's final touch, upgrading the material to a new level, making it not just functional, but more resilient against the effects of time. But the journey isn't over. The panels are immediately sent to a high-speed trimmer. Whirring saw blades slice away the excess edges and any unstable material. Only panels that meet standard dimensions, typically 4x8 feet, or custom sizes for special orders, are retained and proceed. Each cut is both technical and symbolic, marking the completion of the board's form. If hot pressing was the moment of rebirth, then trimming is the rite of passage, where the product assumes the identity of a new, standard industrial material. Fresh from the hot press, the particle board panels are like red-hot metal bars from a forge. They're searingly hot and filled with internal stress. If left alone, the temperature and moisture differential would cause them to warp, crack, or shrink unevenly. This makes cooling an absolutely essential stage. On the conveyor, each panel, still radiating heat, is sent into a forced cooling line. A massive system of industrial fans blows air from all directions, top, bottom, left, and right, enveloping the entire surface. The airflow doesn't just lower the temperature, it also releases the internal stresses in the panel structure, bringing it back to a state of equilibrium. In advanced mills, this process includes two-way cooling with integrated thermal sensors. The sensor system continuously monitors the temperature differential between the core and the surface, adjusting the airflow to ensure the panel cools uniformly. The goal is to prevent the outside from cooling too quickly while the inside remains hot, which could easily lead to cracking. From a distance, the cooling line resembles a long corridor where the newborn panels line up neatly, passing through a fierce rush of industrial air. This moment isn't as loud as the grinding or hot pressing. Instead, it's a much-needed period of calm for the product to stabilize and finalize its form. Once cooled, the particle board is structurally stable. However, its surface is still rough, with jagged fibers and uneven ridges left from the cutting process. Left as is, the panel would be nothing more than a raw industrial block, unfit for modern furniture or construction. This is where the precision sander comes in. A series of massive sandpaper-covered rollers are arranged back to back, spinning at high speed. The panel is fed in, and each roller glides over the surface, sanding away thin layers measured in fractions of a millimeter. A steady low hum fills the air like an industrial soundtrack. A high-capacity dust collection system operates simultaneously, sucking up the tiny wood particles that are released during sanding. This not only keeps the air clean, but also prevents dust from scratching the panel's surface as it cycles through. The result after a few passes is a surface as smooth and flat as a mirror. You can run your hand over the panel and feel the sleekness, a stark contrast to the initial roughness. This smoothness is the foundation that allows the particle board to be finished with melamine, laminate, or paint. Coatings that transform it into the tables, cabinets, and shelving of our everyday lives. This is a testament to the power of technology, the ability to turn something rough into something refined, and to transform a byproduct into a product with aesthetic value. Quality control is the final and most critical step, the ultimate stamp of perfection. This is where human oversight and technology work together to ensure that every single panel leaving the line meets international standards. On the conveyor, each panel passes through a comprehensive laser scanning system. The red beam sweeps across the entire surface, detecting minute cracks, warping, or thickness variations as small as 1 millimeter. These defects are immediately flagged and rejected, ensuring no flawed product reaches the market. Next are the mechanical tests. A random selection of panels is taken to a testing machine where they are bent to measure elasticity, compressed to determine load-bearing capacity, and twisted to evaluate stability. Each data point collected becomes a crucial piece of information, certifying the product's quality to both clients and the market. At the end of the line is the packaging stage. Automatic robots stack the panels neatly like giant bricks, then wrap them tightly in a plastic film to protect them from dust and moisture. A barcode is placed on each package, connecting it to a global warehouse management system. With just one scan, you can pinpoint exactly where and when the batch was produced, and even get detailed technical specifications. But even at this final stage, the story of the environment is still present. Plastic film is difficult to recycle and becomes a burden on the waste system. Therefore, some pioneering factories are experimenting with new solutions, packaging made from compressed fiber paper or biodegradable film. This proves that the journey towards sustainability doesn't stop at recycling wood, but extends to every aspect of production. And so, from what were once worthless wood fragments, through a series of purification steps and challenges, there finally emerge complete panels, flat, solid, and uniform. In warehouses, they are stacked like massive blocks, ready to travel, cross oceans and borders, and eventually transform into dining tables, library bookshelves, or partitions in a modern office. Completion. It's not just a technical stage, it's the final transformation where the rough becomes refined, where what was discarded becomes a valuable product. And it is in this moment that the rebirth journey of wood scraps reaches its fulfillment. The story of wood always begins with a living entity, the tree. Before becoming a beam, column, floorboard, or door frame. It stands silently in the forest, enduring wind and snow, storing decades of growth within itself. In the past, to fell such a tree, it took 2 or 3 strong men, pulling a handsaw or swinging an axe for hours. Today, in the forests that serve the industrial wood sector, the scene is completely different. This job is entrusted to the harvester, what many forest workers call the game changer. Inside the cabin, the operator sits on a seat, hands on the joysticks. When he pulls the lever, the harvesting head closes like a massive hand. The hydraulic saw blade begins to spin. In just a few seconds, the trunk is cleanly severed, falling in a pre-calculated direction. Without waiting for the tree to settle, the cutting head immediately clamps down on the log, pulling it through steel delimbing knives. Branches and foliage are stripped from the trunk, falling as lightly as thin straw. Finally, the computer inside the cabin precisely measures the length and diameter, automatically cutting the log into sections according to the desired order. Waste is nearly zero. What a crew of loggers used to take hours to complete with axes and saws is now finished in 60 seconds with absolute machine precision. Here, the job is handed over to another character, the loader. It lifts each log, swings it halfway around, and places it onto the waiting semi-truck. The driver steps down, inspects each log, and begins the securing process, or strapping tie-down process. Iron chains are draped across like harnesses, and steel straps are tightened using hydraulic tools. Everything must be precise to the last detail, because a small discrepancy on the road could cause the entire stack of logs to slide off, leading to an accident at any moment. When everything is done, the multi-ton vehicle slowly rolls out. The wood's next journey will be to the sawmill, where wild nature begins its transformation into products that serve human life. Our destination is Freeman Lumber. Founded in 1832, this is one of the oldest family-owned sawmilling operations in North America. Currently, this facility processes hundreds of thousands of cubic meters of lumber annually, primarily from 3 key species of Canadian forestry: hemlock, pine, and spruce. The products are distributed not only within the Nova Scotia region, but are also widely exported throughout the eastern United States. But numbers and output are only part of the story. What keeps Freeman Lumber enduring is the family spirit. For generations, members of the Freeman family have directly managed the operation, passing down knowledge and maintaining their reputation through their own name. They also uphold the forest with a genuine sense of responsibility, working with associations, adhering to reforestation regulations, and ensuring that the trees felled today are replaced by new life. And so, the story from the Freeman family opens a door for us. To better understand their values, let's leave the pages of history and step straight into the mill where the real journey begins. When the log trucks drive through the mill gate, they proceed to what can be considered Freeman's raw material bank, the log yard. Before us are thousands of round logs, stacked high in long piles. Here the wood is not just randomly dumped, it is organized by species, diameter, and length. This helps the mill maintain a stable operating rhythm, even when the forest faces storms, deep snow, or logging disruptions. Afterward, the logs are fed straight into the debarker. Here, rotating rollers, gears, and cutting heads tightly grip the log, stripping away the rough bark. From a round log darkened by bark and mud, it emerges with a brighter surface, clearly showing the wood grain. This process may seem simple, but it is extremely important. The seemingly harmless bark can carry dirt, rocks, or grit, things powerful enough to damage the saw blades. In a high-speed operating environment, that risk not only increases blade replacement costs, but also poses a danger to workers around the mill. From here, we continue into the central area of the entire line, where the round logs begin their transformation into boards. The process begins with the head rig saw paired with a chipping canter. Laser scanners map the log's exact shape, and the computer decides the optimal rotation so the highest value wood faces the cutting path. High-speed chipping heads shave away the uneven outer surface of the log, forming a clean-sided prism the industry calls a cant. The cant then enters the twin band saws, a dual bandsaw system with massive cutting power. Combined output can exceed 2,000 horsepower, but the real performance doesn't come from the horsepower. It comes from the thin, razor-sharp blades. The thinner the blade, the less wood is lost to sawdust, and the more lumber you gain from every log. But high speed demands high control. Thousands of boards can be produced every hour, and without proper handling, they'd pile up like a scatter of matchsticks. That's where the unscrambler and singulation systems take over. These machines separate the boards, align them into single file flow, and create a clean, orderly stream so the scanners in the next stage can work with absolute precision. Viewed from above, the moving boards look like people passing through a security gate, steady, organized, and never colliding. Upon leaving the primary sawing area, the surface of the boards is still rough, the edges are uneven, and natural defects exist. To meet commercial standards, they must go through a refinement stage, where artificial intelligence and modern sensors replace the human eye. The flow of rough lumber is fed into the full vision scanner, a system of cameras and lasers operating continuously. The system identifies the wood grain, knot locations, cracks, warp, and even defects that are hard for the naked eye to see. This data is immediately processed by the AI software, which then provides the optimal solution, cutting out the damaged sections and retaining the highest value material. No longer relying on subjective experience, the decision is calculated based on thousands of parameters. The boards, after being edged and trimmed, become neat and square, with the flawed sections removed. Economic value is thus maximized. A single log can yield more standard-grade boards and less waste. After being optimized, the lumber is fed into the bin sorter system, which has over 100 different bins. Each bin corresponds to a specific combination of length, thickness, species, and grade. When a bin is full, the bottom opens and the entire stack of boards drops onto the stacking conveyor below. Each board is precisely aligned. Between every layer of boards, the machine automatically places small wooden pieces called kiln sticks, or stickers. They create consistent gaps so that when the stack is put into the kiln, hot air and moisture can circulate evenly around every single board. Afterward, the stacks of lumber are taken by forklift into the massive kilns. Inside, the entire environment is rigorously controlled. The temperature increases in cycles, the humidity gradually decreases, and high-powered fans alternately reverse direction to ensure even distribution of heat. The goal is to bring the wood's moisture content down to around 10%. The ideal equilibrium level that ensures the wood's stability during storage and use. When it emerges from the kiln, the wood has changed. It is no longer a body part of the forest, but a complete industrial material, durable, stable, and ready for its next journey. This is the premium lumber section, the place where materials are handled under exceptionally strict standards. The boards are pre-sorted, then a forklift feeds them into a dedicated in-feed line. A tilt hoist separates each piece and sends them onto the conveyor. From there, the boards enter the 8-head molder, an industrial planer equipped with 8 cutter heads running simultaneously. In just a few seconds, all 4 faces are surfaced. Dimensions are brought into perfect tolerance, and the grain comes into sharp focus. At that moment, the rough board begins to take on the character of a high-end commercial product. After molding, the boards pass through another scanning system. Industrial cameras inspect every line of grain. AI evaluates where a knot looks appealing, where a crack appears, and where a flaw is unacceptable for this grade. Based on that analysis, the system automatically trims out the defective portions. Each cut represents a balance between final product length and surface quality. Boards are trimmed to common lengths: 6 feet, 8 feet, 12 feet. Finally, the boards are stacked into perfectly square bundles. Automated equipment aligns and compresses the pack so every edge is clean and uniform. The entire bundle is wrapped in white Freeman lumber branded nylon with reinforced corner protectors. By the time they leave the line, they no longer resemble forest wood. They look like finished, clean, premium products, ready for the shelves of major building supply retailers. Not all wood is destined to become decorative material. The mass-market construction industry needs volume, consistency, and performance. That's where the planer mill comes in, the final stage of the entire production line. First, the kiln sticks are removed from each lumber pack and gathered for reuse in the next drying cycles. These little strips of wood seem insignificant, but their reuse reflects the mill's core philosophy. Nothing is wasted. The boards then enter a high-capacity planer. Here, the line can run at nearly 2,000 feet per minute. Rough edges and slight warping from the drying process are shaved away. Each piece is brought back to precise, industry-standard dimensions defined by building codes. After planing, the boards move through another full-vision scanning system. AI sorts them. The highest-grade pieces continue forward, while boards with defects are reassigned to other uses, shorter cuts, structural applications, where appearance doesn't matter, or specialized grades. Before leaving the planer mill, every board is stamped, usually with a blue or red ink mark. The stamp carries essential information: wood species, mill ID, technical classification, and structural grade. It's essentially the board's diploma, certifying that it's ready for work in construction with the full confidence of architects and engineers. Finally, the bin sorter arranges lumber by size and grade. When a batch is complete, the boards are stacked, compressed, strapped with steel bands, and wrapped in white protective film to guard against moisture and dust. From Nova Scotia, bundles bearing the Freeman Lumber logo are loaded onto trucks and ships, traveling thousands of kilometers to the eastern seaboard and beyond. There, they reach distribution yards, hardware stores, workshops, and home building sites. In those lumber yards and carpenters' shops, Freeman boards begin a new journey, becoming foundations, door frames, and rooftops for countless families around the world. Upon leaving the planer mill, one feels as though the traditional lumber journey is complete. But in the modern world, beyond the familiar boards, there is another line of material that is gradually changing the way people build homes: engineered wood. Next, we will leave Canada and travel to the Pohlmeier factory in Germany, which produces LVL, laminated veneer lumber, from beechwood. Unlike the dry log yards in North America, this mill sources beech within a radius of about 150 to 200 kilometers, then keeps the logs continuously misted in the yard. The moisture prevents surface checking, insect damage, and fungal growth. In other words, the wood doesn't age too quickly before entering the production line. Before it becomes veneer, the beech is debarked, cut to standard lengths, and placed into large heating vats. Hot water and controlled temperatures soften the fiber structure, allowing the veneer to peel smoothly with minimal cracking. Offcuts, such as end pieces or unsuitable sections, are chipped and sent off as biomass fuel, wood fiber, or raw material for charcoal. Once again, no part of the tree goes to waste. On the peeling line, the log is clamped at both ends and spun like a giant pencil, while the stationary knife blade presses tightly against the surface. A thin veneer layer, only about 3.5 millimeters thick, unrolls steadily, seemingly endless, as if the log would never run out. Compared to traditional sawing, this method utilizes nearly the entire volume of the tree. The fresh veneer is cut to standard widths and fed into high-capacity dryers. After reaching the desired moisture content, the sheets are sorted by quality and then coated with phenolic resin, a durable glue that withstands time and harsh conditions. The glue-coated veneer layers are stacked with all wood grains running in the same direction. This is the key difference between LVL and conventional plywood. While plywood typically has layers cross-laminated to increase stability, LVL has all grains running parallel, creating a material with very high load-bearing capacity in one direction. This multi-layered veneer block enters a massive press. Under a temperature of about 100 degrees and immense pressure for several minutes, the adhesive is cured, bonding the veneer layers tightly together. The result is a dense, long, homogeneous LVL panel, virtually free of the major defects found in natural solid wood. From a mechanical standpoint, LVL can achieve strength comparable to, or even exceed, steel in specific applications. Yet it is lighter and performs well in timber structural systems. It becomes an ideal material for beams, headers, and load-bearing elements in large timber buildings. Viewed from a distance, you might only see a long wooden panel, but inside is a combination of natural wood, the chemistry of the adhesive, and the logic of structural engineering. The wood here is not just forest wood, but a high-tech engineered material. Not every mill is as large as Freeman or Pohlmeyer. The wood industry also has countless medium-sized facilities where modern technology and traditional methods stand side by side. One of these is the lean Hartsberger mill. Its scale may not match the industry giants, but its process follows a similar logic, ensuring optimization from the tree to the board. A log's journey begins right in the log yard, where spruce and fir trees are received, unloaded, and neatly stacked in layers. They pass through the debarker, shedding their outer layer, and then proceed to the cut-off saw, or bucking saw, to divide the trunks into neat sections that match the desired dimensions. From here, the wood enters the most critical stage, sawing. This large vertical bandsaw has enough power to slice through the entire log, separating the main wood block and the side boards. The main block is then transferred through an edger and a resaw for final shaping. Once a stable shape is achieved, the boards are stacked with spacers, stickers, and then moved into the kiln to remove excess moisture. The hot air helps tighten the wood fibers, and upon exit, they are transferred through the planer so that the surfaces become flat, smooth, and sharp-edged according to standards. In the final stage, the boards are sorted by quality. The most beautiful ones are reserved for flooring, cabinetry, or applications requiring high aesthetics. The more modest boards are well suited for structural framing or pallets. The whole process is like an upgrade journey. From a rough log, the wood has been transformed into a complete material ready to enter human life. In another factory within the wood industry, the panel production line operates with a steady and precise rhythm. The goal here is not to create thick dimensional lumber, but thin veneer sheets, the foundation for plywood, furniture, and decorative panels. The log begins its journey through the debarker. Immediately afterward, it enters the rounding machine, which is tasked with adjusting the log's roundness and balance before veneer peeling. This stage sounds simple, but determines the stability and uniformity of the future veneer. If the log doesn't spin perfectly round, the veneer will be inconsistently thick and thin. The heart of the line is the veneer lathe. The log is tightly clamped at both ends and spun at high speed, while a long knife blade presses against the surface. In just a few seconds, the first layer of veneer is peeled off in a continuous ribbon. The veneer ribbon runs along the conveyor belt, soft when freshly peeled, with a faint scent of raw sap. The veneer ribbon continues to the guillotine cutter. The guillotine knife drops with decisive strokes, cutting the veneer into individual sheets of standard length. Each cut is as precise as if guided by a ruler, allowing the veneer sheets to fall neatly into the stack below, all perfectly aligned. Finally, the automatic system collects and stacks the finished veneer sheets. The stacks of wood are uniform, neat, and ready for transport. Though thin and light, each veneer sheet is predetermined for a significant role, becoming the bright surface layer of tables and chairs, living room wall panels, or a part of the load-bearing plywood inside a house structure. That is what makes panels one of the most important materials in the modern interior world. The journey we have just completed, from the deep forests of Nova Scotia to the panel lines in Europe, from ultra-modern factories like Freeman Lumber to medium-sized mills like Lean Hartsberger, reflects a simple yet timeless truth. Wood is not just a material, it is the result of labor, engineering, and a profound understanding of nature. From a distance, the wood industry may seem to only revolve around sawing and wood chips, but the deeper we look, the clearer we see two parallel streams: the power of machines and the competence of humans. Machines provide speed, precision, and maximize resource utilization. But it is the human who looks at the log and sees its potential. Moreover, this is also a reminder that technology, no matter how sophisticated, cannot be separated from the philosophy of sustainable forest management. The longest-lasting mills, like Freeman Lumber, are precisely the ones that understand this better than anyone. The forest is not a green quarry that we exploit until depletion, but a cycle. If we care for it, it will give us good material year after year, generation after generation. The wood industry is constantly changing, from the axe to the harvester, from the handsaw to AI, from solid wood to engineered wood. But the goal has never shifted: to create the best material from humanity's oldest renewable resource. Thank you for joining us on this journey to explore the inner world of wood, a world that is rough yet full of logic, powerful yet subtle. And thank you to the craftsmen, the engineers, and the machines that contribute to creating the boards, beams, and panels that modern life relies on every day. We look forward to seeing you in the next stories, where the sound of the machines still rings out, the smell of wood is still new, and people are still working diligently in the forest, in the mill, and among the cuts full of meaning. This is Rawmachines. Goodbye, and see you next time. Welcome to Rawmachines, your journey to discover the most impressive processes around the globe. Today, let's dive into the production process of laminated veneered lumber, or LVL. This is more than just a building material, it's proof of how humanity can spectacularly refine, multiply, and surpass the inherent limits of natural wood. Particle board isn't just an alternative material, it's like the Earth's response to the era of climate change. If wood waste is buried in landfills, it decomposes and produces methane, a global warming gas 25 times more potent than CO2. But if it's collected and recycled, this problem is significantly mitigated. For every ton of recycled particle board, we save around 12 mature trees from being felled. This preserves forests, provides a refuge for birds, and maintains the flow of biodiversity. What's more, particle board offers significant economic benefits. Compared to solid wood, it's cheaper and easier to mass produce. Consumers benefit, businesses save costs, and the entire supply chain becomes more seamless. It's a clear symbol of the circular economy, where nothing is discarded as waste, but instead, resources are simply waiting for a new purpose. Now, let's join Rawmachines for a deep dive into how this process works. Every piece of particle board starts with what seems like a worthless resource: dusty sawdust from the corner of a mill, wood shavings from a saw blade, scraps from old furniture, or even planks from dismantled buildings. Typically, softwood is the ideal choice due to its uniform structure and ease of processing, but occasionally hardwood is also utilized, although it requires more effort and energy.